We continue with the second part of the lecture on assemblers with the assembler logic and the discussion of a possible implementation. Let's look at the overall assembler logic. So what the assembler needs to do to translate our assembly code to machine language. Okay, we suggest that it works like this. First, it needs to parse an assembly command, that is, break it into its underlying fields. For example, an A instruction has the underlying field of this value or symbol. A C instruction has more underlying field, right? For example, destination and computation. So what do we need to do with each of these instructions? If we have an A instruction, then the symbolic reference that we find in the A instruction has to be replaced with the corresponding memory address. This will be symbol handling, and we discuss it later. For C instructions, after parsing for each of the field in the instruction, we need to generate the corresponding binary code. Finally, we assemble the translated binary codes into the 16-bit machine instruction and write the 16-bit instruction into the output file. Okay, so this is how the assembler will work. We'll process the assembly program from line to line. So let's see what symbol handling requires. We also call it as symbol resolution. Remember, we use symbols, labels, and variables to refer to memory and instruction memory locations. We have predefined symbols and user-defined symbols. Predefined symbols, right, this is agreed. These predefined symbols are agreed for hack assembly and hack machine language. They are the virtual registers from R0 to R15 and some predefined pointers that we will use later on in the software hierarchy. Then we can have user-defined symbols, labels. They are destinations for jump instructions, that is ROM addresses, and variable symbols, RAM addresses. Remember, RAM addresses starts from 16. Why? Because the first from 0 to 15 addresses are dedicated for predefined symbols. Okay, so here we can see some examples in this code for labels and for variable symbols. Okay, so the main step of symbol handling is to generating a symbol table and of course using it later on. Okay, the symbol table will contain the predefined symbols, will contain labels, and will contain variables, will contain the symbolic reference and the value of the memory address. So how do we handle this symbol table? As for predefined symbols, they can be filled in before the assembly process. Label symbols. Again, label symbols are destination for jump. They are ROM addresses. These addresses start from 0 and increase for each instruction, but not for label declaration. Label declarations like loop, write, they disappear in the machine language code. Now, label symbols can be referred to before or after declaration, right? So here we declare loop, for example, and here we refer to. But for example, for write, it is the opposite. We refer to write here, but we declare it here. Therefore, to have a simple assembler process, we will introduce a first pass where we only resolve these label symbols and fill them into the symbol table. Variable symbols, they are RAM addresses, and it is agreed in hack that these symbols get RAM address sequentially as they appear in the program, starting from 16, as the first 0, 15 locations are used for predefined symbols. Okay, and well, this memory will be allocated when this symbol is used first, and it will be allocated during the main assembler pass. Okay, so this is what we suggest to do. We will have an initialization phase where we create the symbol table and add the predefined symbols. Then we have a first pass. This first pass does not generate any machine language code, it just fills in the label declarations and addresses into the symbol table. Okay, it will be a pair of the name of the label and the address in the instruction memory. Then in the second pass we process the assembly code line by line. If it is a C instruction, we parse the instruction, code the parts, put them together and write the output file. If it is an A instruction, when XXX is simply a number, then we simply replace it with a binary value. If XXX is a symbol, then we either find this symbol in the symbol table and then we replace it with the address, the binary value, or we cannot find this symbol in the symbol table, then we have to allocate a memory location for this symbol and insert the information into the symbol table.